Okay, so let's consider the question. A cylinder contains 0.5 meter cube of steam at 4 bar and 200 degrees Celsius. If the steam is cooled at constant pressure until the volume becomes 0.1 meter cube. Question says find the mass of the steam and calculate the final dryness fraction, work done, and heat transferred. Okay, so this question actually gives us two conditions. We have first the conditions at state 1. So let's get the parameters or conditions at state 1. Okay, so we were given a cylinder contains 0.5 meter cube. So initial volume, okay, V1 equals 0.5 meter cube. Okay, at 4 bar. So initial pressure P1 equals 4 bar, okay, and 200 degrees Celsius. So initial temperature, okay, T1 equals 200 degrees Celsius. Then we're also giving conditions at state 2. Okay, so they say if the steam is cooled at constant pressure to a volume of 0.1 meter cube. So final volume, which is V2, 0.1 meter cube, also cooled at a constant pressure. If the steam is cooled at a constant pressure, so pressure is constant, P1 equals P2. P1 is same thing as P2 and is given as 4 bar. Okay, that's all. First question says find the mass of the steam. So of course we'll use the condition of the steam at state 1 to find the mass of the steam. Okay, so from we're given temperature given, okay, T given is given as 200 degrees Celsius. That's at state 1. So what we'll do now is to find the saturation temperature at this pressure and see if this steam is actually superheated or saturated. So from saturated water and steam, table corresponding to 4 bar, that's the given pressure, let's find saturation temperature now. This saturation will be, all right, so let's search this is saturation water and steam. Okay, this is saturated water and steam. We are looking for 4 bar. This is the pressure column. Okay, so this is 4 bar, which is here, so not forgetting. Okay, this is temperature column. This is temperature column. Okay, so 4 bar, the saturation temperature is 143.6 degrees Celsius. Okay, so this saturation is simply 143. Okay, saturation temperature is 143.6 degrees Celsius. Okay, so we notice now that the given temperature is greater than the saturation temperature. So T given is greater than T saturation. Okay, so which means steam is superheated. Okay, that means steam is superheated. Okay, since the given temperature is greater than the saturation temperature, it actually implies that the given that the steam itself is actually superheated. And for superheated steam temperature, initial dryness fraction is simply 1. Okay, so therefore X, which is dryness fraction, is simply 1. So in order to obtain the mass, so we know that volume, which is V1, must be total volume at state 1 must be equal to the mass times initial, this is X1, that's initial dryness fraction, X1, times Vg at 200 bar. So we are going to now find the volume of the gas at 200 degrees Celsius from superheated steam temperature, because the steam or the condition at state 1 is superheated. So we move now from superheated steam temperature, from superheated steam table. Okay, from superheated steam table corresponding to 4 bar and 200 degrees Celsius. So let's find what Vg is at 4 bar 200 degrees Celsius. So we'll move now to superheated steam table, degrees Celsius. Okay, let me zoom this a bit. Okay, let me zoom this a bit. Already saturated water and steam. This is superheated steam table corresponding to 4 bar. So this is the okay. So if we take a look at this, we'll have this is pressure on top, then under is what temperature in degrees Celsius. So that means this is actually pressure, and what you have under is temperature. This means this is pressure 0.17, what you have under is 7. Okay, so at 7 degrees Celsius the pressure is simply 0.01. so that's what it means. All right, so we're looking for 4 bar 200 degrees Celsius. So this is 2 bar, this is 3 bar, this is 4 bar. Okay, so from 200 degrees Celsius, this is a column for 200 degrees. Okay, 4 bar happens to be the last pressure here. Okay, so this is the column for the temperature. This is 10 degrees, this is 100 degrees, and we are looking for 200 degrees Celsius. Remember I said the first is always given as VG, so this is actually V, this is actually VG, that's specific volume. So at this given temperature 200 degrees Celsius, let's trace down now to get 4 bar. Okay, this is 4 bar, this is 4 bar, that's the pressure 4 bar, and this is 200 degrees Celsius, right? Oh yes, so that's 200 degrees Celsius. Okay, so that means the value for specific volume is simply 0.5345. okay, so the first is always VG, specific volume, so you have that to be 0.5345 200 degrees Celsius. Okay, so VG is actually 0.5345. okay, VG equals 0.5345 meter cube per kilogram, since it's specific. Okay, so that is the value of specific volume at 200 degrees Celsius at 4 bar and 4 bar. Okay, at the superheated steam. So now V1, which is total volume at state 1, is equal to mass times dryness fraction at state 1 times specific volume at state 1, which is VG or VG1. Call this VG1. Okay, so to make mass subject, this simply implies mass is equal to specific total volume at state 1. Mass is equal to total volume at state 1 V1 all over dryness fraction at state 1 times the value of specific volume of the gas. So this is not equal to the, remember, initial volume was given to us, that's the volume at state 1 was given as 0.5. so you simply have 0.5 divides by dryness fraction is 1 superheated times VG times VG, which is 0.5345. okay, all right, so this is simply, you said mass is equal to 0.5 divided 0.5345. that simply implies that mass itself is 0.94 kg. that gives us the mass of the steam. Okay, so next question says to find the final dryness fraction. Okay, next question says to find calculate the final dryness fraction. Okay, so to do that, of course, that should be at state 2. We are given condition at state 2. The question says okay, if the steam is cooled at constant pressure, so which means if the steam is cooled, it becomes saturated, so water sets into the steam, it becomes saturated. So they are asking us to find the final dryness fraction. So since steam is cooled, okay, since steam is cooled, okay, so which means we have to go to at constant pressure, remember, okay, at the pressure still remains as P2 still remains 4 bar, same thing as the first pressure. So we need to now go to saturated water and steam table to find the value of VG. Okay, so from saturated water and steam, we have a corresponding to 4 bar. So we need to find what VG is. This becomes VG2. Okay, since that's at state 2. Alright, so we'll go to saturated water and steam table now. So I'll zoom this a bit. Okay, this saturated water and steam. We'll look for 4 bar. Okay, remember this is the VG line, that's volume at the gas. That's the third line. Okay, so this is 4 bar. Okay, this is VG. Value is simply 0.4623. Okay, 4 bar is 0.4623. You have that. All right, so VG is equal to this is 0.4623 meter cube per kilogram. So this gives us the specific volume at state 2. Not also forgetting, volume at state 2 was given V2 as 0.1 meter cube. So using the same relationship, final volume at state 2 is simply mass times the dryness fraction at state 2, which we're asked to find now, multiplied by this volume, a specific volume of gas at state 2. So we know VG2, we know the mass of the steam now. We need to make X2 subject. So that simply implies that X2, which is the final dryness fraction, is simply total volume at state 2 divided by mass times VG2. So this is equal to V2 is 0.1 all over mass was gotten to be 0.94 multiplied by VG2, and VG2 is simply 0.4623, so we'll have times 0.4623. okay, so X2 final dryness fraction is 0.1 all over 0.434562. okay, so therefore 0.1 divided by this simply gives us the final dryness fraction. X2 is simply 0.23. That gives us the final dryness fraction. Okay, next question says calculate work done and heat transferred. So let's go for the work done now. Okay, so to calculate work done, of course, in thermodynamics, work done is an integral from initial volume V1 to final volume V2 of pressure times change in volume. So this is work done. Okay, so work done is equal to integral. The initial volume was given as 0.5 from the question. Okay, initial condition at state 1, initial volume is 0.5. okay, final volume was given as 0.1, so you simply have that. Okay, so you have 0.5, final volume is 0.1. okay, pressure was given as 4 bar, which is 4 by 10 to the power of 5. okay, so 4 bar is simply 4 by 10 to the power of 5 times change in volume, so times dV. okay, so as always, whenever you're integrating, simply bring out constants out of the integral sign. So we'll have 4 by 10 to the power of 5 integral from 0.5 0.1. You're left with dV. okay, so this is equal to 4 by 10 to the power of 5. If I integrate dV, I will simply have V, so from 0.5 to 0.1. okay, so having this now, work done is now equal to 4 by 10 to the power of 5, okay, into, so we start with upper limit minus lower limit, and upper limit is 0.1, so you simply have 0.1 minus lower limit is 0.5, so you have 0.5. okay, so this is equal to 4 by 10 to the power of 5 into 0.1 minus 0.5, that's approximately minus 0.4. okay, minus 0.4. okay, so therefore work done is equal to, so if we multiply this together, we'll have, okay, so 4 by 10 to the power of 5 multiplies minus 0.4 simply gives us minus 160 by 10 to the power of 3 in joules. So this simply implies that work done is minus 160 kilojoules. So you have this now. So you notice that they said water, the steam became cooled. Okay, so if the steam became cooled at constant pressure, that means heat has been removed from the system. That's why you have negative value as the answer. So it becomes the work done. Okay, final question says we should find the heat transferred. Alright, so the last part of the question says we should calculate the heat transferred. Okay, alright, from first law of thermodynamics, Okay, we have that heat supplied minus work done is equal to change in internal energy, simply du, or you can simply say heat supplied minus work done is simply equal to U2 minus U1. So let's find the internal energies. Okay, so U2 stands for the internal energy at state 2, while U1 stands for the internal energy at state 1. Not forgetting that the condition of the system at state 1 shows that the steam is actually superheated. Alright, so go to superheated steam table to obtain the value of internal energy. So from superheated steam table, okay, corresponding to, remember the pressure is simply 4 bar, so corresponding to 4 bar, temperature given at state 1 is also 200 degrees Celsius. So corresponding to 4 bar and 200 degrees Celsius, the value of the internal energy at the gas is same thing as the value of the internal energy at state 1. So internal energy at the gas shows us the internal energy at state 1 for superheated steam. Alright, so we'll go to the superheated steam table now. This is superheated steam. So corresponding to 4 bar, we have this to be 4 bar. Okay, I told you this is this shows pressure. The values on top are pressure, the values beneath are temperatures in degrees Celsius. Okay, so we have the temperature lines here. This is different temperature range. This is 200 degrees Celsius, what we're looking for. And remember, the second line, the first line is always specific volume, which is this. So you see Vg. The second line is specific internal energy, that's at the gas Ug. So the second line always shows specific internal energy. Okay, so we're looking for 200 degrees Celsius, which is this, corresponding to 4 bar. Okay, this 200 degrees Celsius corresponding to 4 bar. Okay, here, so this is 4 bar, second line Ug, so the value is 2648 kilojoules per kilogram. So the internal energy Ug, and that's equal to U1, is simply given as 2648, so 2648 kilojoules per kilogram. So this happens to be the specific internal energy at state 1. Now, alright, so since the steam is saturated at state 2, and we need to find internal energy at state 2, we'll simply employ recall the relationship between dryness fraction and internal energy is simply given. So this is dryness fraction at state 2. S2 is simply equal to specific internal energy at state 2 minus internal energy of the fluid at state 2 all over UFG state 2. That's internal energy between the fluid and the gas. So if I make U2 subject, specific internal energy at state 2 becomes X2 UFG2 plus HF2. So all I need to do now is look through the saturated water and steam table, obtain UFG and and UF. Okay, obtain UFG and UF at state 2. So from saturated water and steam corresponding to 4 bar, so we'll find Ug. Okay, so this is saturated water and steam. Alright, okay, this is superheated. This is saturated water and steam corresponding to 4 bar is this. Okay, so please take note, these are the values of internal energy. So this is UF and Ug. Okay, so let's obtain the value for 4 bar. This is 4 bar, which is this. Okay, this is 4 bar. This is UF. Let's confirm. Yeah, that's UF. 4 bar is 605, while Ug is 2554. So at 4 bar, UF itself, okay, Ug is 2554. So we have 2554 kilojoules per kilogram, while UF is simply 605. Okay, 605 kilojoules per kilogram. So all we need to do now is to find UFG, and UFG itself is simply Ug minus UF. So we simply have okay, 2554 minus 605, that gives us UFG and at state 2, and that's equal to, okay, so that's equal to 1949 kilojoules per kilograms. Okay, so we've gotten UFG, so we can now substitute into this equation to find specific internal energy at state 2, and that's simply the dryness fraction at state 2. We got dryness fraction at state 2 to be 0.23 multiplies UFG, which is 1949, okay, plus UF plus UF gave us 605, okay, plus 605. So specific internal energy at state 2 is equal to 0.23 multiplies 1949, and that is 448.27 plus, okay, 605. So this simply means that specific internal energy at state 2 is actually, okay, if we add these two together, we'll have 1053.27 kilojoules per kilogram. So we need to convert this to total. Okay, we can keep it like this. So change in internal energy now. Change in internal energy, the U is actually U2 minus U1, and that's equal to U2 give us 1053.27 minus U1 is the specific internal energy at state 1, and we obtain that to be 2648. So we'll simply have this to be minus 2648. Okay, 2648. Okay, so specific internal energy at state 2. So U2 specific internal energy at state 2 is simply minus 1594.73 kilojoules per kilogram. So this gives us change in internal energy, please. So this is change in internal energy. So this is specific, so we need to convert to total value. So converting to total value simply multiplies mass by change in internal energy. So that simply mass is 0.94 multiplies minus 1594.73. So total change in internal energy is now equal to, okay, so we have minus 1499.0462. This becomes in kilojoules. So we can now employ first law of thermodynamics, Q minus W equals change in U. Okay, so let's make Q subject, and that's simply sending W over here. So we simply have change in U, total internal energy plus work done. Okay, so heat transferred is equal to, the total internal energy was giving us minus 1499 minus 1499, okay, points 0462, and work done, we obtained work done as minus 160 kilojoules. Okay, we obtained work done as minus 160 kilojoules. Okay, so in place of work done now we simply have minus 160 kilojoules. All right, okay, so therefore heat supplied is actually equal to, okay, that is 1659.0462 kilojoules of heat. Please minus 16. Okay, so as always, the reason why we have negative sign is simply because heat was removed from the system. So heat removed from the system is actually negative, so that's why we're having negative. All right guys, that's it to that question. I hope you enjoyed this video. Please do share your thoughts in the comment section. I will see you in the next video with more questions on working fluid. Please do stay tuned to the channel, subscribe if you're new to this channel, and I will see you in the next video. Thanks.